coordination polymerization system. It is unfortunate that my recording system was not working properly. I couldn't record your class yesterday and today. In fact, I tried to record it, but after 40 minutes after completion of the class, I came to know that the sound was not recorded, and again I have to record it. Anyway, coordination polymerization, we have already discussed free radical polymerization and anionic and cationic polymerizations. Now another type of polymerization is coordination polymerization. So here the word indicates that coordination complex will be formed or a catalyst system that contains an organometallic compound and that reacts with the monomer unit and it forms a monomer catalyst complex. And this monomer catalyst complex is acting as a the reaction center for the next incoming monomer. In fact, the metal carbon bond will be established in the monomer catalyst complex. The metal atom of organometallic catalyst and the carbon atom of the monomer units will bonded together, and then the new incoming monomer will interact with the metal atom and then form a bond with the metal atom, and here the subsequent incoming monomers will also interact with the metal atom, and subsequently the propagation stage will continue, and finally the stage is the termination, as you know. Now let us discuss point by word by word. The polymerization reactions. POLYN means it is an abbreviation of polymerization. It is my own abbreviation, not a universal abbreviation. Polymerization reactions, especially of olefins and dienes, catalyzed by organometallic compounds, fall under the category of coordination polymerization. The first step in the polymerization process is the formation of a monomer catalyst complex between the organometallic compound and the monomer. The reaction scheme is shown here. So this part RCH2 empty means metal, it is representing metal. This is an organometallic compound or organometallic catalyst, and this is reacting with a monomer. For example, we have taken 1,3-butadiene, CH2 double bond CH2 double bond. So once the carbon atom of the monomer or pi electron density of the monomer is interacting with the electron deficient metal atom, and then it forms an extended bond between the carbon of the monomer and metal atom of the catalyst. And here we get a monomer catalyst complex if the organometallic catalyst is interacting with the monomer unit. So we are getting a cyclic complex, and subsequently the new monomer will come which interacts with the metal atom and the reaction will continue. Here the MT represents transition metal such as titanium, molybdenum, chromium, vanadium, nickel or rhodium, etc. So in the formation of this monomer catalyst complex, a coordination bond is involved between carbon atom of the monomer and the metal atom of the catalyst. Hence the polymerization effected by such catalyst system is called coordination polymerization. The coordinated metal carbon bond formed in the monomer catalyst complex acts as the active center from where the propagation starts. As I already told, the metal carbon bond in this complex is acting as the active center for the further polymerization reaction. The incoming monomer is incorporated at the active center of the metal carbon bond. So that is why incoming monomer is incorporated between the carbon metal bond. So that is why it is called the active site. Here the reaction is shown. So here we have taken the catalyst monomer complex, and here what happens is this carbon metal bond is broken and then it forms a CH2 metal bond with the new monomer unit. Okay, and then what happens is this extended bond will partial bond will shift towards the carbon-carbon bond. So this will become a carbon-carbon double bond, and this partial bond will shift towards this. So this forms a covalent bond between this carbon and this carbon. So here you can see that the new compound, it is RCH2, RCH2, and then this CH2 is this CH2, and then this CH double bond. So here we have a double bond. So we get double bond here and this CH2, and then this CH2 is represented here as this CH2, and then what remains is the metal ion. And in the next stage, another monomer unit will come. So that will interact with the pi electron density of the monomer. Next incoming monomer will interact with the metal atom, and then again it forms a complex, just like what we had seen earlier. And again the same process will continue, and then the propagation stage starts. The new monomer is getting incorporated between the metal and the new the old monomer carbon atom. The metal atom in each step forms coordination bond with the monomer carbon. In coordination polymerization, the catalyst monomer complex is a heterogeneous system. This is mainly because of the presence of the metal ion. So here for the polymerization reaction we normally use a solvent. So in that solvent the organic part will be dissolved and the metal part will not be dissolved, that will be in the solid state. So this is a heterogeneous system with the metal ion in the solid phase and the carbanion of the alkyl group in the solvent phase. So it is shown here, the metal is in the solid phase, this is electron deficient, positively charged, and more electron density will be there, so this is negatively charged, that is why it is called the carbanion. And the monomer is inserted in between the metal ion and the carbanion, with the result that the polymer chain formed is pushed out from the solid catalyst surface. So here you can see that the metal carbon bond is the active center of the polymerization. Here the catalyst is shown in the solid phase and rest what is shown in the solvent phase. New monomer will come, monomer will interact with the metal atom and is getting incorporated in between. So here M1 is the new monomer, and the second monomer M2 will come, it will interact with the metal atom, getting incorporated between this metal and the next first monomer, and then we get M2 M1 CH2R, and the third monomer will come, it will be incorporated here, so we get MT M3 M2 M1 CH2R, etc., and so on. So here if you look at this reaction, you can see that the first monomer is pushed more away from the metal ion, and the second monomer again pushed away, and the third monomer again pushed away. So the new monomer is very close to the metal ion, and the old monomers already part of the polymeric chain will be pushed away from the metal ion. Here M1, M2, M3 are the first, second and third monomer units. In certain catalyst systems, depending on the polarity of the metal carbon bond and on that of the solvent medium, the metal counterion is placed in a particular spatial arrangement with respect to the anion, and this leads to stereoregular polymer formation. The well-known example is Ziegler-Natta catalyst. The major advantage of coordination polymerization is the formation of a stereoregular polymer. That means we get a very specifically isotactic polymer or syntactic polymer by using the coordination polymerization. So by any other methods, it's not easy to prepare the stereospecific coordination polymerization. For example, if you take polypropylene polymerization, so propylene contains a CH3 group as the pendant group, and if the CH3 groups are all directed towards only one direction, then we are getting isotactic polymer. And if the CH3 groups are alternatively in two different positions in the space, then we get a syntactic polymer. So for the preparation of isotactic or syntactic polymers, we can use coordination polymerization method. The major important class or major important example of coordination polymerization is the Ziegler-Natta catalyst. So the Ziegler-Natta catalyst was used for the preparation of stereospecific polymers and also unbranched polymers. Earlier, the people were getting by using the cationic or anionic or ionic polymerization, and by the free radical polymerization, they were able to obtain the branched chain polymers. Sometimes it may not be used, it may not have fine applications, or it may not have the desired properties. So they have used the Ziegler-Natta catalyst. It was discovered in 1950s. Ziegler and Natta, two scientists, and after the discovery of Ziegler-Natta catalyst, there was a big boom in polymers, particularly synthesizing the desired kind of polymers with the molecular weight, stereo regularity, etc. And here in Ziegler-Natta catalyst, we have one catalyst system and a co-catalyst system. Two types of compounds are reacting together to form a complex. So here catalyst is normally the metal atom from group 4 to group 8 halides, and then co-catalyst is normally alkyl, aryl or hydrides of group 1 to 4 metals. It is not 3, it is actually 4. You may correct it as 4 metals. Okay, and these two are reacting together, and then it forms a complex, and from this complex the new monomer will come. It will interact with the catalyst metal atom, mostly titanium. So if we normally talk about Ziegler-Natta catalyst, we normally take triethyl aluminium and titanium trichloride, and for the representation of the mechanism also we are normally using this. There are several Ziegler-Natta catalysts are possible, because you have the freedom to change the metal ion, and you have the freedom to change the alkyl groups or the hydrocarbon part also. So there are several of them are possible. So for our convenience, we normally take triethyl aluminium and titanium tetra or trichloride. Yes. Triethyl aluminium in combination with the titanium trichloride are by far the most commonly used aluminium alkyls, act as the electron acceptor and the electron donor. So here normally aluminium is electron deficient species or electron acceptor, and titanium is the electron donor, and the combination accepts and the combination therefore readily forms coordination complexes, and the complex formed it is missing there, so I have to check it. Yes, the complex formed is insoluble in the solvent and is hence heterogeneous in nature. So normally this will be a heterogeneous catalyst system. One of the structures of the complex is represented as, here you can see that triethyl aluminium R group represented the ethyl group. So and then titanium trichloride, here the aluminium of the co-catalyst forming a bond with the chlorine of the halogen or chlorine of the catalyst, and then titanium metal of the catalyst is forming a bond with the carbon of the co-catalyst. So this forms a cyclic complex. The active center from where the polymer chain growth propagates are formed at the surface of the solid surface of the catalyst complex, and the monomer is complexed with the metal ion of the active center before its insertion into the growing chain. So here it means that in fact the reaction is taking place at titanium carbon bond. So this is the reactive center over here. Okay, and the titanium or the metal ion is in the solid phase, and the reaction is taking place at the surface of it. Okay, and then it propagates. Natta, he is a scientist. Natta, I think he is an Italian. Natta proposed the bimetallic mechanism. Bimetallic means there are two metal ions are there in this mechanism involved, So it is a bimetallic mechanism. As the catalyst and co-catalyst components are mixed, there occurs a chemisorption of the aluminium alkyl. Chemisorption of the aluminium alkyl in this part on the titanium trichloride solid surface. So chemisorption of this part on the titanium trichloride is taking place, resulting in the formation of an electron deficient bridge complex. Here you can see that it is just like a bridge complex of the structure shown above. Then the monomer is then attracted towards the titanium carbon bond. Here this is the titanium carbon bond in the active center when it forms a pi complex with the titanium ion. So here you can see that titanium is electron deficient, and then this CH2, because this CH2, this is electron density is high, and this will become CH2 minus, and then if this bond is shift towards or interact with titanium and forms a bond with it, complex form with it, and then this carbon will become a negative, positively charged. So that is what this carbon is positively charged, and this bond breaks towards this carbon atom, and this carbon will become negatively charged. And then the further reaction will take place, and then we get a transition state like this. So this transition state should be established, and then from there new monomer will come, and it will interact with the titanium, and it will be incorporated in the growing chain. The bond between R and titanium opens up. So here it opens up, producing an electron deficient titanium. So that is why it forms electron deficient titanium. So it gets the freedom to interact with the electron rich CH2 double bond CH group. Okay. The titanium ion attracts the pi electron pair of the monomer and forms a sigma bond, while the counter ion attracts the electron deficient center of the monomer. So here what happens is titanium, if it breaks, this will be R minus and this will be plus. So the counter ion minus and plus is here. So what happens is it will, if you take it from the top side, you can see that CH2, this CH2 attached with titanium, it will be electron deficient, and then this carbon, once it goes, this carbon is positively charged, it is shown here, and the counter ion will attack the electron deficient carbon, and then it forms a transition state. The monomer in this way is inserted into the transition state ring structure, and this transition state now gives rise to the chain growth at the metal carbon bond, regenerating the active center. So this process repeats itself. This transition state, every addition of every monomer unit, the transition state will be established, and the propagation of the addition of the monomeric unit will take place, and this transition state will establish, incorporation of the new monomer unit will take place, and this process will continue throughout. So here you can see that here exactly the same process is taking place, and then this transition state complex is formed exactly like what we got in this case, previous case, and then again we get a transition state, and the transition state is represented here, and the process is going on. The monomer units are getting incorporated between titanium and this carbon atom of aluminium, triethyl aluminium. Okay, so here this process will go on, and we will get a big monomer unit, big polymer unit. Here you can see that the CH3 groups are the pendant groups in this case. Here you can see the CH3 group as the pendant groups, or the side groups are represented towards the upside. All CH3 groups of the propylene is represented as the represented upwards, because to identify the tacticity of this polymer formed, if all CH3 groups are represented towards the upside, and then it is isotactic polymer. So here we are getting an isotactic polymer, but getting isotactic and syntactic polymer is a different issue. There are several factors depending on it. So we'll discuss it. And repeating the whole sequence will give the growing polymer chain. The monomer insertion is repeated in this manner, and the orientation of the substituent group of the monomer is always taken from the metal ion end, resulting in a stereo regular polymer. So this can be explained as follows. Actually, this happens. How this happens? Stereo regularity is maintained, or stereo regular polymer is formed, is mainly because titanium is electron deficient, and the vacant d orbital will be there, and every time monomer will get added, and then transition state will be generated, and then every time the new monomer will come, the vacant d orbital will regenerated. If the vacant d orbital regenerated will be on the same side, then we normally get isotactic polymer, and if the vacant d orbital is regenerated in opposite direction alternatively, then we get syntactic polymer. And this also depend on several factors like interaction of the incoming monomer with the alkyl group, substituent groups of the monomer already present in the polymeric chain, and also the incoming monomer and the chlorine atom of the catalyst. So we will discuss it. When the vacant d orbital of titanium atom regenerates at the same position all the time, the incoming monomer unit will be inserted with the same spatial rearrangement, resulting in the formation of an isotactic polymer. We have already discussed it. With the insertion of each monomeric unit, if the d orbital migrates from one position to the other alternatively, the monomers get inserted with alternating spatial arrangement, resulting in the formation of a syntactic polymer. Whether the active site is regenerated at the same position or migrates to the other site alternatively would depends on the interactive forces existing between. There are two things, or two interactive forces are mainly determining it. Several other things like temperature, pressure, solvent system, etc. will also decide the stereo regularity of the polymer formed. The first interactive force is the substituent group of the incoming monomeric unit and the already inserted monomeric unit. There will be an interaction between the incoming monomeric unit and the already inserted monomeric unit. And then another interaction is the incoming monomer unit and the chlorine atom of the active catalyst. So these two interactions will be there, and also there are several factors like catalyst system, catalyst crystal structure. All these have profound effect on it, and molar ratios of the catalyst, co-catalyst components, and temperature of the reaction influence the shift of the migration of the vacant d orbitals, and hence the stereo regularity of the polymer formed. So stereo regularity of the resultant polymer depends on several factors. Two factors are the interaction of the incoming monomer with the monomer already present in the growing polymer chain, and also the incoming monomer with halogen of the active catalyst, and also the temperature of the reaction, crystal structure of the reaction of the catalyst, and molar ratio we have taken, and molar ratio of the catalyst to co-catalyst system, and also the type of catalyst employed. All these depends on all these deciding the factor of, are the deciding factor of stereo regularity of the polymer. And whatever be the structure of these active complexes and mechanism of active center formation, the polymerization is characterized by the initiation, propagation, and termination as follows. As we know that polymerization reactions normally represented as initiation, propagation, and termination. Here also in coordination polymerization also these three processes are taking place. The first process is the initiation process. Here we have a active metal alkyl center, and the monomer unit is there, and here monomer units is interacting with the metal carbon bond of the active center of the metal alkyl group, and then we get monomer is inserted, or incorporated between the metal and the carbon of the active center. That is the initiation stage, and then subsequently more number of monomers will come and that will be incorporated into the metal carbon bond. The propagation stage, there are several number of monomers will come, and then the repeating units are represented. And then final stage is the termination. It can be brought about by any one of the three given process. It can be done by three process. Sometimes it will be terminated by itself, otherwise we need to add something inhibitor like of compounds to stop the reaction to control the molecular weight and all. So here you can see that the propagating polymer is represented here, and if we add an active hydrogen compound, or if it present the active hydrogen compound, the R dash will go with the metal atom, and this CH2 will become CH3. Okay, so here you can see that R dash. Here you can see that the metal CH2 bond will take up this proton, and R minus will go with the metal atom. So here you can see that empty R is formed, and this CH2 will become CH3. So one end is CH3 and other end is R. The repeating unit is the same, CH2 CH CH3. And termination by transfer with a monomer. So here you can see that a monomer is near to it, but here the termination is taking place instead of propagation. So here you can see that the carbon hydrogen bond shift towards this carbon carbon bond, and the metal is formed a bond with the monomer unit, and then carbon carbon double bond is established at one end of the growing polymer, and the reaction stops. So here a stable compound is organometallic complex is compound is formed, and then we have a polymer arrested by carbon carbon double bond established at one end and R group on the other end. Next is termination by spontaneous internal transfer. So here actually what happens is the carbon metal bond picks up this proton, and then this carbon hydrogen bond shift towards the carbon carbon. It will again establish a carbon carbon double bond at one end, and here we get a metal hydrogen. And what are the advantages of Ziegler-Natta catalysis? The major advantage of Ziegler-Natta catalysis is the stereo regular formation of the stereo regular polymer, and also the branched, we can avoid preparing the branched polymers. So these two are the major advantage of Ziegler-Natta polymerization. Traditionally, polymerization of alpha olefins was done by radical polymerization, and the problem with this technique was that the formation of undesirable allylic radical formation leads to branched polymers. In fact, we sometimes do not need branching, then we should not need to go for radical polymerization. For example, radical polymerization of propene gives branched polymers with large molecular weight distribution. Large molecular weight distribution means if we prepare a polymer, or if we synthesize a polymer, there will be different polymeric chains will be there, and if one chain of polymeric chain of molecular mass of 50,000, and suppose if you have another polymeric chain of mass molecular mass 1 lakh, and another one 2 lakh, another one 3 lakhs, another one 5 lakhs, etc. So there will be huge difference in the molecular weight in polymeric chains. So if there is a huge difference in the molecular weight in different chains, we may not get a desired property of the polymer. So that is what the molecular weight distribution. Also, radical polymerization had no control over stereochemistry. So the stereo selectivity or stereo regularity can only be achieved by organometallic or coordination polymerization method. Linear unbranched polyethylene and stereo regular polypropylene could not be prepared by radical polymerization. Ziegler-Natta catalyst can give linear alpha olefin polymers with high and controllable molecular weight. Moreover, it makes the fabrication of polymers with a specific tacticity possible. That's what we have already discussed. Polypropylene, PP is polypropylene, cannot be polymerized by free radical mechanism, but stereoregular polypropylene can be prepared with a Ziegler-Natta catalysis. So Ziegler-Natta polymerization is a method of vinyl polymerization. What are the other advantages of Ziegler-Natta catalyst? High selectivity possible and high efficiency possible, high stereoregularity possible, and longer lifetime of the polymer possible, high concentration of the polymer product and lower cost in production, and then easy regeneration of the catalysts and controls growth and formation of the polymer product. That means we have a good control over the molecular weight of the polymer and control of polymer particle morphology in spherical shape. Particularly we can synthesize in the spherical shape, and then higher stability. And the Ziegler-Natta polymerization can also be done in heterogeneous phase and homogeneous phase, but normally heterogeneous phase is employed. Even though we have very simply talked about Ziegler-Natta catalysis, the catalyst systems are not easy to handle, truly speaking. It is highly sensitive, highly moisture sensitive, and if you are not keeping it properly, and if you are keeping it a highly humid place and all, it will explode. So while handling this catalyst, we have to be extremely careful.